Imagine computing in the 1970s. Long before our smartphones and ultra-thin laptops, these massive machines occupied entire rooms. A typical computer center looked less like a modern tech hub and more like a refrigerator factory. These physical behemoths housed a massive maze of separate interconnected parts. For the engineers maintaining them, they were a logistical nightmare. They had to manually wire hundreds of separate integrated circuits together. If just one connection shook loose among the thousands of cables, the whole system would refuse to work. Even early chips like the older Intel 8080 were physically demanding. The 8080 required 3 separate power supplies, a +5, -5, and +12-volt line just to function. Computing power was limited by its own physical footprint, a maze of hardware that had to be consolidated, if it was ever going to move from the factory floor to the desktop. In 1976, Intel released the 8085. It packed what used to be a room's worth of logic into one single chip. It immediately solved the power supply headache. Instead of requiring 3 separate lines, the 8085 only needed a single 5-volt supply to run. And for the era, it was highly capable. This small piece of silicon could process instructions at 3 megahertz, meaning it executed 3 million clock cycles every single second. You can think of the 8085 as the grandpa processor. By tearing it down, we can see the structural logic that still defines how digital devices work today. To understand how it works, picture a computer system as an active factory. You have raw materials entering the input unit, moving into the central processing unit where the work happens, interfacing with a memory warehouse to store data, and finally shipping out through the output unit. Inside that factory, the processor needs to find materials. It uses the address bus, a navigation system with 16 dedicated lanes. Because it uses 16 bits, it can calculate exact coordinates for over 64,000 distinct memory locations. Once it finds the right location, it uses the 8-bit data bus. Think of these as an 8-lane highway of delivery trucks physically carrying the actual data payloads back and forth. Without these specific bus networks routing the traffic, the CPU would be isolated from its memory warehouse, unable to process a single instruction. If we look directly at this 8085 architecture diagram, we can see the internal storage right on the chip. On the right side, the register array features blocks labeled B, C, D, E, H, and L. These act as tiny, temporary pockets to hold active data. Over on the top left is the accumulator, also known as Register A. This is the boss register, where almost all of the calculations and logic operations are staged. To manage all these tasks, the chip uses a stack pointer. It organizes memory exactly like a spring-loaded stack of cafeteria plates. The last piece of data placed on top is the very first one to be removed. Right in the center is the arithmetic and logic unit, or ALU. It acts as the internal math teacher. Right above it sits the flag register, a status reporter that flips specific bits to let the processor know if the recent math resulted in a 0, a negative number, or generated a carry. All of the processor's work is a highly coordinated routine, shuffling data back and forth between these internal pockets and executing basic arithmetic. Every action the 8085 takes is governed by the fetch, decode, execute cycle. First, the processor fetches a specific instruction from the memory grid. Next, the internal circuitry decodes that instruction so the processor understands the exact command. Finally, the ALU executes the required mathematical or logical task. That is the core rhythm of computing. The 8085 performs this simple read, understand, work loop millions of times a second, continuously, without ever sleeping. By today's standards, those specs seem tiny. The entire 64 kilobyte memory capacity of the 8085 is so small that a single high-resolution selfie taken on your phone would instantly overwhelm it. Yet, despite being decades old, the 8085 remains a universal starting point in engineering schools. Because its architecture is visible and relatively simple, it clearly exposes the mechanics driving modern hardware. You learn to ride a bicycle before a motorcycle. By the time you've mapped the movement of data across these 40 pins, all the billions of invisible operations happening inside a modern smartphone finally have a concrete place to land.